Okay. First of all, I would like to thank the organizers for the invitation to speak, and particularly Rafael. So let me begin by recalling or stating a special case of a conjecture of Darmon-Roger that will be relevant for this talk. Okay, so I'm going to take EA rational elliptic curve. Conductor N. I'll denote by F the associated new form. Okay, so meaning that the Hasse-Weil L series of E is the same as the Hecke L function, the standard L function of smaller form F. And I'm going to take P, a prime of good ordinary reduction for E. Okay, and one more piece of notation. I'm going to take K over Q and imagine a quadratic. Okay, and it will be assumed to be of discriminant prime to NP. Okay, so I'm going to make the following assumptions. So first, I want the prime P to be splitting K. Okay, and secondly, that if I write n as product of n plus n minus with I put in n plus the primes dividing n which are splitting K, and in n minus those that are inert. When I do that, n minus is square free and consisting of a not a number of primes. Okay, and the motivation for this last assumption is that so this implies that if I look at the L series of E base change to K, this will have sign +1 in its functional equation. Okay. So still it's a bit more notation. So I'll let phi be a finite order character. Okay, and I'll be fixing throughout embeddings from Q bar into QP bar and C. So just for simplicity, I'll assume that this embeds into QP. Okay. So this will be a finite order character. GK is the absolute Galois group of K. Yes, so it's the absolute Galois group. Yeah. Okay, so finite order character of conductor prime to NP. Okay, and now I'm going to consider two weight 1 forms. Okay, so I'll get G to be the theta series attached to phi. Okay, so first of all, let me denote by alpha phi p and by beta phi p bar. And so I'll denote by calligraphic x the set of following set of height 1 primes. Okay, so this will be okay, so I'll explain this notation in a second. So this will be certain height 1 primes in the one variable power series ring over ZP, and where I let k run over integers at least 1 and theta p power root of unity. Okay. So when I have such height 1 prime, the integer k is by definition what we're going to call the weight. Okay, so now I can consider following weight 1 theta series attached to phi. And what I can do is I can choose one of the roots, alpha or beta, of its Hecke polynomial at p, and p stabilize that. That will give me a p ordinary form, which by a theorem of Wiles and Hida, I can put it fits in a Hida family. Okay, so I'll denote by G, which you should think of as a family of forms parameterized by these points in calligraphic X. This is a Hida family. With G of X naught equal the alpha stabilization of G okay, for some X naught of weight 1. Okay, so the weight of X naught is 1. And I'll do the same for a dual form. Okay, so I'll denote by H the theta series attached to the inverse character, and that will analogously fit in a Hida family with H of some x0 equal the alpha inverse stabilization of H. Okay, so I have F attached to our fixed modular form, and now I have considered these two weight 1 forms, which I will put in a family both G and H.
What is x0?
X0 is some point in weight space, so that when you take the corresponding element in the Hida family, it recovers the alpha stabilization of G.
It's a fixed element?
Yeah. So when I put G in a Hida family, there will be some unique X naught, so that the corresponding element in the Hida family recovers the alpha stabilization of G. Okay. So in this setting, we have the following result of Darmon and Roger. Okay, so there exist the following three elements. First of all, a p-adical function, LPF, in this one variable power series ring, such that this can be evaluated at any of the primes in calligraphic X. And when I do that, I recover essentially the square root of a special value, the central value of a triple product L function. Okay, so I'll denote that by L alg f g of x h of x. And this interpolation property takes place at the points x of weight 1. So that's one of the ingredients. There will be 2 more. So secondly, there is a big cohomology class attached to the triple F and the Hida families G and H. Okay, so this is a global cohomology class defined over Q. And
sorry, can I ask, so is every element of this family G a theta series?
Not necessarily, but I can pick. Well, not necessarily, but I think using some result of Belaishe and Dimitrov, one in fact knows that they will all consist of CM forms. But at least I can certainly pick a Hida family consisting of CM forms passing through this weight 1 theta series.
Because if you don't do that, then does this LC?
Yeah. So certainly I need to, for this interpolation property to uniquely determine this element, I need to have infinitely many specializations. And in order for that to be possible, that forces G and H to be a Hida family of theta series. I can always guarantee that that's the case if I start off with weight 1 theta series as in here. Okay. So there is a global cohomology class. And this will take values in the triple tensor product. So BP of E is the p-eighted model of E tensor QP. And then G and H will have attached some big Galois representations. And this class lives in this triple product. And its defining property is that now I can similarly specialize this class at any weight x. And this essentially will recover some Abel-Jacobi images of diagonal cycles. Okay, so I'll denote this like so. And this holds for all points in weight space of weight at least. Okay, so if you look, for example, at the case of weight 2, these diagonal cycles will essentially be coming from a diagonal embedding of a modular curve into a triple product of modular curves. Okay, for higher weights, you have to do a similar construction at the level of Kuga-Sato values. Okay, and the third ingredient that will actually connect the two is a linear map, a Perrin-Riou big logarithm map, which is now a local map. So it's defined on H1 QB with values in the same triple product representation. Taking values in ZP double brackets T, the same ring where our p-adical function lives. And the property of this map is as follows. So there is this with, if I pick an arbitrary class, kappa underline in this triple product, I can evaluate it at this class. So it gives me an element here, which I can evaluate at any point in weight space. And that map will essentially recover the p-adic logarithm of the corresponding specialization of the class, kappa of x. And this will be the case provided the weight of x is at least 2. And if I look at the points of weight 1, I'll recover instead the block-Kato dual exponential map applied to this class. Okay, so these are the three ingredients, and the main result is that via this map, the p-adical function and the cohomology class are related. Okay, so these three elements are such that our p-adical function, LPF, arises as applying the Perrin-Riou big logarithm map to the restriction at P of this global cohomology class. Okay?
So here the difference between log and exponential is somehow from some local behavior of the class.
Yeah, so the fact that this map has different interpolation properties depending on the weight will allow us to say something about the local properties of this class. Okay, that's actually one of the next things I'm going to say. Okay, because for example, for weights at least 2, these classes arise from a geometric construction, so they will be certainly lying in the Selmer group. But when you specialize at this degenerate weight somehow, they may not be crystalline anymore. And in fact, one of the outcomes of this equality is a criterion for deciding when the weight 1 specializations of these classes stay crystalline at P. So, okay, so let me make the following definition first. Okay, the generalized Kato classes will denoted by kappa twiddle alpha inverse. Okay, and these are just what you obtain when you take these classes, kappa, these big cohomology classes, specialize at geometric weight, so weights at least 2, but now you let the weight go to 1. Okay, so you let x approach this point x naught, where I recover the weight 1 forms, h and g. Okay, so this will give me a class, a global cohomology class, now taking values in B and tensor with BG, BH, which are some Martin representations. Okay. So, okay, and here I made a choice. I chose alpha and alpha inverse, but you can imagine how similarly you would define three more classes. Okay, and maybe I need to assume that, that alpha is not equal to alpha inverse or beta inverse. Okay. All right, so we have that. And now going back to this equality, one immediate corollary is what I was saying in words. These classes that you obtain by this p-adic limit process will be Selmer. Precisely when the restriction at P is in the block Kato finite subspace, but that's precisely the kernel of the dual exponential. Okay, but now when you specify a weight 1, this recovers the L value. So that will be precisely the case when this central value at 1 is trivial, vanishes. Okay. Okay, so so I explained this construction in this particular setting. But this is actually a special case of the construction of Darmon and Roger. They would start with some Artin representations, irreducible of degree 2, and you can kind of play the same game and end up having a class in this triple product. Okay, but we're going to exploit the features of our setting. Okay, because one thing you note is, so in our case, this triple tensor representation will actually break as a product with a direct sum of induced. So this will be induced from K to Q of the trivial character direct sum induce K to Q of some character that denote by psi, which will be a ring class character. Okay, so okay, and similarly, this triple product L function will break up as a product of two. Okay, so this will imply that L F G H S will be L E S, its quadratic twist, and the L series of E base change to K twisted by psi. Okay, so as a corollary of this theorem, we know when these classes are Selmer, and an important thing to note is that so this L series will have sign +1. Okay, so if this L function vanishes at 0, in fact, it vanishes to order at least 2 at s equal to 1. And the conjecture of Darmon and Roger that I want to state is precisely telling you that precisely when this vanishes to order 2 is when these classes will be non-trivial. Okay, so so for that, yeah. So as I'm going to state in a second, yeah, this class should be non-trivial precisely when this vanishes to order 2 at s equal to 1. But so in our case, we are interested in elliptic curves of rank 2. So we're going to put ourselves in a situation where the order of vanishing 2 is concentrated in this factor. Okay, so similarly, what we're going to do is we're going to look at the projection of these classes into the part coming from the elliptic curve. Okay, so I let K alpha inverse in H1 Q BP of E to be the image of this kappa twiddle under this projection. Okay, will correspond to the fixed point and the reaction of complex conjugation of H1 over K. Okay, so the special case of the conjecture of Darmon-Roger that I want to state is the following. Okay, so suppose, as I was saying, that the order of vanishing is concentrated on the factor coming from the Hasselblad series of E. Okay, so assume that L for the quadratic twist doesn't vanish at 1, and same thing for the third factor. Okay, so okay, so if you put yourself in this situation, then the following should be equivalent. Okay, so first of all, the order of vanishing of the L series of E at 1 is exactly 2. Second is that the dimension of the p-adic Selmer group of E over Q is 2. Okay, so the 2 and the 1 and 2 are equivalent is essentially BSD in this case. Okay, so the new input is this third equivalent condition, namely at the span. Okay, so here I define explicitly what kappa of alpha is, but you do the same for the others. Okay, so you actually get 4 classes, a priori distinct, and because we assume that L vanishes, these classes will land in Selmer. And they should span a non-trivial subspace so this subspace is non-zero precisely when 1 and 2 hold.
Should it have rank 2?
Yeah, so one consequence will be that there will be some linear dependencies between these 4 classes. Okay, so I'm not claiming that.
But will it always have rank 2? It's never rank 1, like conjecturally.
So this always should have rank 2.
But the span of those classes.
Yeah, will be one-dimensional conjecturally.
Oh, it will be one dimensional.
Yeah, that's the next thing I'm going to write. Yeah, that's one of the surprising features of this conjecture, that a natural guess would be that these 4 classes exhaust the entire Selmer group, but in this particular case, they should all line up on a canonical p-adic line on Selmer. Okay, so in that case, up to QP cross, we should have the following. Okay, so kappa alpha alpha inverse should be p-adic log of Q, P minus p-adic log of P, Q. Kappa alpha beta inverse should actually be trivial. Kappa beta alpha inverse should be trivial as well. And finally, kappa beta beta inverse should be again the same expression. Yeah, that's the next line. Okay, where PQ is a QP basis of the p-adic Selmer group. Okay. Okay. So now that if you apply p-adic log to this linear combination, it trivially gives you 0. So conjecturally, these 4 classes should span this canonical p-adic line given by the kernel of the p-adic logarithm.
Is there a conjectural recipe for the some complement of this line?
Not conjectural, but if I don't know if I will get to that, but yeah, so to produce a class in the complement, all you need to do is produce a class whose p-adic logarithm is non-zero. And we have some way of showing the existence of such class under some additional hypothesis. So what do I want to say next? Yeah, so just to emphasize what I said in words. So one thing is that the span.
So the assumption is that this is a QP basis with this property.
No, any QP basis will have this property.
So it's really invariant. If it's true for one, it's true for every other one.
Yeah, because this is just giving you a basis of the kernel of p-adic log. Yes. Okay, so conjecturally, the span of these generalized Kato classes this conjecturally should be the kernel of p-adic log. Okay, inside Selmer.
Is it trivially contained in? Showing that it's in the kernel is something trivial? Or?
It's not trivial. It actually follows. So the next remark I'm going to make is that there are some results of Darmon-Roger where they produce 2 linearly independent classes in Selmer by producing, but it's for the triple product, and they compute the p-adic logs of these classes. So from the norm-vanishing of these p-adic logs, they get that their classes are linearly independent. But in our case, these p-adic logs are 0. Okay, so in our cases, the result of Darmon don't apply precisely because the p-adic log of these classes will be 0 in our case. Okay, so yeah, the next remark was precisely on that. Okay, so the rank 2 rank 2 results of Darmon-Roger are in situations where one can show that two generalized Kato classes are linearly independent. Okay, and the way they produce such classes is by explicitly computing the p-adic log of these classes, and they will make some assumption that will guarantee that this p-adic log is non-zero. Okay, and that's how they can explicitly exhibit two linearly independent classes. But in our case, these p-adic L values that control the p-adic logarithm of these classes, they will be 0, so the result won't apply in our setting. Okay, so the fact that at least these classes do lie in the kernel of p-adic logarithm in our setting can be deduced from the work of Darmon and Roger. Okay, but still, it could be that these classes they all collapse to 0. So they actually, what one has to show is that these classes are non-zero in our case. Okay. So, okay. Okay, so let me state what we can show. Okay, so I'll denote by k infinity over k the anticyclotomic zip extension of k. Okay, so this is a Galois extension of K, whose Galois is isomorphic to ZP, and the action of, so if I denote by gamma the Galois group of this extension, this is the one which has a property that the action of the non-trivial automorphism of K over Q will act as inversion on the elements of gamma. Okay, so by the work of Darmon and Roger from the mid-90s, sorry, Bertoni Darmon from the mid-90s, one knows that there exists an element in this Iwasawa algebra for this group, characterized by another interpolation property. Okay, so when I denote by this the value of this theta element at any character, this recovers essentially the square root of the L value of E of S change to K, S equal to 1, for all finite order characters, finite p power order characters. Okay. So our theorem now can be stated as follows. This is John Ward with Minglung Xie. So suppose that the p torsion of E is irreducible as a GQ module. And ramified at all primes dividing n minus. Okay, remember n minus were the primes which are factors of n which are inert in K. So if this element vanishes to order precisely 2 at the trivial character, then the dimension of this p-adic Selmer group is 2. And we have the expression for these generalized Kato classes in terms of P and Q as conjectured by Darmon and Roger. And okay, and the other two expressions as predicted by Darmon Roger. Okay, so in the remaining time, I would like to sketch, at least indicate the main ingredients of the proof.
So the quadratic twist, somehow the L value is non-zero, that's a consequence or assumption?
Yeah, so it's under these assumptions where we have the conjecture formulated. Okay, so the L value of the quadratic twist is non-zero, and the L value, so L E k at 1 is non-zero, and L E over k psi at 1 is non-zero. Okay. So yeah, so this condition is actually playing the role of the condition 1. It's just that we don't have a way of getting our hands on a second derivative of Archimedean L series, but the p-adic ones, thanks to Iwasawa theory, are more accessible. Okay.
So psi is somehow auxiliary, like in the statement there is no
Yeah, psi is auxiliary, yes. But this indeterminacy in QP cross will essentially come from the algebraic, will include as one of the factors a contribution from this L value, so will depend on psi. Any other questions? Okay, so let me sketch the proof. Okay, so the main idea is that what we're going to do to get, so first of all, this equality will be an easy consequence of the main conjecture. Okay, so what's going to take most of the work is establishing this equality, and that will be obtained by computing this second derivative at the trivial character in 2 different ways. Okay, so the idea is compute this second derivative at 1 in 2 different ways. Okay, so the first one will be a consequence of the main conjecture. Okay, so the first one will be using the anti-Sekotomic main conjecture. Okay. So what's the relevant Iwasawa module in this setup? So we're going to look at the following. So we have the usual P infinity descent Selmer group. Okay, so our K infinity is the union of this Kn, where Kn has degree P to the n over K. And we're going to look at the limit under the restriction map and take the Pontryagin dual. Okay. this is naturally endowed with structure of a module first over CP and then the action of the Galois group up the tower. And I'll denote this by X P infinity. Okay, so this is a module over this, finally generated. And the main conjecture predicts that it's in fact torsion, and its characteristic ideal is generated by the square, okay, because our third element interpolates square roots. Okay, and this is now a theorem under the hypothesis stated in this first line. Okay, so by the work of Bertolini, Darmon, and Skinner-Urban. Okay, so maybe yes, so okay, so by this we know that X P infinity is torsion. With its characteristic ideal. Is a principal ideal generated by the square of this third element. Okay, so this equality of characteristic ideals by a so-called control theorem tells you something, allows you to relate the order of vanishing of this adjectival character to the rank of some associated Selmer group. So that's what I'm going to do next. Okay, so letting SP of k, SP of E over k. Okay, so here I was taking torsion coefficients. Here instead, I'm going to take compact modules. Okay, so I'm going to look at the p to the n descent Selmer group over k. And now I take the projective limit under the multiplication by p maps. Okay, so so if you want this is now a ZP module, and to kind of relate that to the notation I was using earlier, when you tensor this ZP module with QP, you cover what I was denoting before as the Selmer group for BP of E. Yes, thank you. Okay, so letting this by descent, okay, it follows, we have the following. So the order at the trivial character of this, the square of this third element, which is what interpolates DL values. You may wonder why I work with the square root, but actually it's key that we have these squares. Okay, so this is at least this quantity. Okay, so RP is by definition the CP rank of the compact Selmer group I just introduced. And plus and minus are the ZP ranks of its plus and minus eigenspaces under complex conjugation. Okay, so okay, so that's what I'm denoting. RP plus minus, and okay, so this is nothing but twice the maximum of RP plus RP minus. So one gets this inequality for on the one hand, and moreover, if I denote this by rho p, one has a formula for the image of this element in this power of the augmentation ideal. Okay, so that if I look at this element square, one has a leading term formula. Okay, so which will involve the p primary part of the Tate-Shaffer-Abich group of E over K divided by its maximal divisible subgroup. Okay, so this is by construction finite, and some regulator, which is actually a derived regulator. Okay, so I'll say more about this in a second. And this is an equality taking place in here. Okay, so and up to p-adic units.
So I can't read what you
Which part?
the last line.
Yeah, so this is I, which I'm going to introduce in a second, is the augmentation ideal for gamma,
Power.
and the power is this. Yes. Okay, so this first equality is just telling us that this element lives in this power of the augmentation ideal, and in fact one can give maybe if I know by bar the image in the quotient, but the next power of the augmentation ideal, one has this equality.
Can you say a word about why you get this strange formula of twice the maximum of?
Yes, in a second. In a second. Yes, that's again another key point.
Supposing like Shah is finite.
Yes, but so I could have said assume Shah is finite, and then I forget the diff. But I also get this formula without assuming that. But then what shows up here is this thing, which is like the block Kato Shah. Which
Is this like some Iwasawa version of Shah, or like because the left hand side like is Iwasawa like periodical function, like actual power series?
yeah. So originally, to get this thing, what you do is you work with the characteristic ideal of the module, but by the main conjecture that's the same as taking the square of the theta element. Okay, so what is I first? So I is by definition the augmentation ideal. And now what is this derived regulator, which will actually address this strange thing on the right hand side? Okay, so R is actually made up of, it's a product of two regulators really. Okay, so R1, R2, and this is a regulator of symmetric anticyclotomic height, a p-adic height, on this SP E over K. But actually, as I'll be indicating in a second, this anticyclotomic p-adic height has some degeneracies. Okay, so I'll denote by SP upper 2 the null space of this height. And then on this null space, one has a derived height. Okay, so that's used to define the second factor here. Okay, so this will be a regulator. But now of a pairing will instead will be alternating p-adic height on SP2 E over K. And I can say a few more things. So in fact, this one is valued in I mod I square tensor cube. And this derived is actually valued in I square mod cube. Which probably cannot be read from. Okay, so here said, yeah, it's this second p-adic height is valued in I square mod I cube. So
I cubes.
Sorry, what?
Just like, and R1 is in this I mod I squared, then
Yes.
the other thing is I squared mod I cube. So when you
Yeah.
multiply, we just
Yeah, so actually this regulator will have as many, it will be a determinant of this height on a basis for this module. And actually this will have dimension, the minimum of RP plus, RP minus. And this will have dimension RP plus, RP minus in absolute value. And we will multiply that by 2. So when you add these two, you'll get precisely rho p. Yeah, and that answers, I hope, Richard's question. Okay, so why is it important to consider these derived regulators? Why do they show up here? Is that, so if I call this height this one, and this one by upper 2, by the Galois equivariance of this height, if I let tau be a complex conjugation, this will be the same as tau pq. Okay, but this is an element in I mod I square, tensor Q if you want, which is isomorphic to gamma. But now tau in gamma acts by inversion, so in additive notation, this is minus pq. Okay, so this is telling you that if you take p and q to be on the same eigenspace under the action of tau, these spaces will be isotropic. Okay, so tau equal to plus minus 1 are isotropic under this p-adic height. And therefore, its null space, which okay, so this is actually the null space. Sorry, we just got a bit cramped here, but null space of the p-adic height. This will have rank at least the difference of these dimensions in absolute value. Okay, so the rank over Zp of the null space upper 2, okay, which maybe I can rewrite here, is by definition the null space of the usual anticyclotomic p-adic height is at least Rp plus, Rp minus. Okay, so that's in sharp contrast to the situation in the cyclotomic case. In the cyclotomic case, one expects the height to be, the p-adic height to be non-degenerate. So there is no such things as derived heights. In the anticyclotomic case, it's a rather different situation. We have actually systematic degeneracies as soon as the plus and minus eigenspaces under complex conjugation have different dimension, but somehow one can make up for that by defining p-adic heights on the null space. So, okay, so I'm almost out of time. So yeah, I'm just erasing, but the way we're going to get our main result is computing the second derivative in two different ways. And so going back to our situation, where we're assuming this guy to vanish to order 2, we get the following. Okay, so just okay, so let me here running out of time. So let me just say that this condition plus that inequality plus this non-vanishing allows you to show that, in fact, in this case,
Sorry, I'm sure you said, what was Kn?
Kn is the nth layer in the anticyclotomic Zp extension. So Kn over K has degree p to the n. Okay, so this Rp plus Rp minus is, in fact, 2, 0. Okay, so in particular, this shows that in this case, Sp, the null space of the first p-adic height is in fact everything in this case. Okay, and out of this formula we get therapy at the trivial character is up to a p-adic unit the determinant of this times the order of SHA. But now using that this is alternating, this actually reduces to the square of the height of P and Q. Okay, so you get, and this should be a square. No, this is good. Sorry, this should be square. Okay, so we get a first formula for the second derivative. And let me just say where the second is going to come from. And it's in fact where we need to work harder. Okay, somehow this first part was just putting together results in the literature, but with some work. Okay, the second is using a variant of Rubin's height formula. Okay. So how does this go? So our assumption that this value doesn't vanish. By comparing the interpolation property of the two p-adical functions that have appeared, one can show that the one attached to the triple product is essentially this Bertolini-Darmon theta element times some element u for some u in QP cross. Okay, and this u will involve this value. But now, on the other hand, by Darmon and Roger, we know that this arises as the image under a Perrin-Riou map of this big homology class. Okay, and so that's precisely a situation in which one can apply a formula a la Rubin when you have a p-adical function which arises as the image under some linear map like that of a family of homology classes. And when you look at the class in the base, you get something that vanishes, as in our case. This vanishes a trivial character by Rubin's formula. Okay, so Rubin's original formula was done in the cyclotomic case, cyclotomic setting. Here we need an analog for some height 1 Lubin-Tate formal groups. Okay. And what that formula lets you do is it shows that kappa alpha alpha inverse lands in this space. Okay. So the fact that the second derivative vanishes the fact this vanishes to order 2 tells you that this will live in the second derived in this space, but in our case we've just shown that this will be the same as Vp of E, cell of Vp of E, and you get a formula for the heights. Okay, so n second derivative of the trivial character times p-adic log k is kappa alpha alpha inverse. And this is true for all kappa in here, which is the same as this space. Okay, so now you have these two different formula for this, and you get the expression in the conjecture of Bertolini-Darmon, Darmon-Roger, by just writing in QP and compare the two expressions. Okay, and once you play these formulas against each other, you directly see that A will be a QP star multiple of p-adic log of Q, and B a QP star multiple of p-adic log of P. Okay, so I'll just stop here. Sorry for running a bit over time.